Thank you, Chairman. My name is Jinsung Park. It's from the Hanyang University. I'm very happy to be here to take the MOOC award this year. Also, the achievement is basically atomic layer deposition for the emerging display application. Since I moved to the academics, actually before moving to the academic, I'm working in the Samsung display, and at the time is my boss is don't think about anymore ALD. This is not academic. This is the industry. So I got a PhD in the thesis from the ALD for the semiconductor application. But unfortunately, moving on, I'm still pushing my research topic to using the ALD for the future. So this slide, I'm very happy to share. So over the 20 years, what I think is what I imagine is the ALD futures in the display. So the limited time, so I'm not going to the deep dive to explain the whole matter in detail, experimental. But however, I made this kind of the 4 topics why we consider ALD, as well as I divided the first, second, third wave in the display, how we can use ALD as a new process. Okay, probably the people know or not is what is the ALD, is the atomic layer deposition. Sometimes familiar, but ALD is the very similar kind of the CVD, chemical vapor deposition, because they're using the precursor and the reactant, which is we are using the chemical reaction. However, the ALD is not unlike the CVD. We're not using the simultaneously inject those both precursor and the reactant. We are divided in the exposure on each surface. That's we expected the sequential and self-limiting on the surface. And also this year is a very anniversary, 50 years anniversary is born in the ALD technique is from the Finland. Actually, I like the brief ALD history, but I want to comment a little bit. The Korea has a big, achievement in the ALD. Especially, he mentioned about the silicon dioxide as a thin film encapsulation. We are using the plasma ALD. Actually, the plasma ALD, especially direct plasma ALD, is born in Korea. Actually, I got his first PhD thesis in the time. My boss is, died by lung cancer, but he actually sold to this technology to the ASM. ASM make money more because of this technology. Okay, you may visit this, the bottom side website, the Netherlands oil and gas groups to make this kind of the table. You may click and you can see the many papers. These elementals, actually all elementals, we are trying to find the ALD process, not only single element like a pure metal, but also compound oxide, nitride sulfide. So you may easily find their kind of thing, okay? And this is I'm just want to mention about the ALD is how to progress for the high volume mass production, okay? Actually, this is not published yet, but this is for too long. This is we are going to publish the Nature Method Primer, but anyhow, this is under revision. But you can see the 1974, the ALE, that time is atomic layer epitaxy, not deposition. It's born in Finland. And that time is actually, they were using the thin film aluminum layer, like a display application, inorganic display. That's the born in, the region is the ALD process, not semiconductor. After that, middle 19th, the semiconductors find out this technology is very slow, but this very, the compound deposition, any kind of the 3D structure. So that's the reason is that they are adopting the very fastly DRAM, aluminum oxide as a capacitor, and the high K metal gate is for the logic devices. Now it's moving on, so the semiconductor field, they're very necessary to the ALD process. However, like, the people are concerning, the ALD is very slow and the throughput is low and expensive. So no one tried to use this ALD technology after semiconductor. However, the PERC solar cell, they're using the aluminum oxide for the passivation layer. They're using the ALD and now it's mass production. And the very, the anniversary kind of 2019, the OLED display first adopted he already mentioned the previous former, the plasma ALD-SiO2, not single layer, is adding in the conventional thin film encapsulation. So they're basically 4-layer adapting. That's the 38 inches plastic OLED, in the Escalade is from the General Motors. So at the times, our group is to work together with the LG Display for 5 years to screening silicon precursors, which is the better. So what I think is the future of the ALD process in the display application, I just write down this kind of structure like a passivation, the buffer layer on the substrate, as well as the active matrix devices. However, even though I think that this kind of the possibility, but we need more like a help for like a precursor material companies and equipment, and also the chip maker, panel maker, as well as the academic researcher. So this is the like a cross section of the brief, the AM OLED structure, and you can see there is like the blue and the red rectangular. What I think is that is the first time. What I think is a possibility, strong possibility. When I use the ALD, maybe there is a strength. Okay, so one thing is the ALD is slow, so we're not going to the more thicker. We're going to the thinner, as well as the uniform. Okay, 8 generation is fine, as well as the most ALD strength is to control the exactly thickness, composition, as well as the property. So let me move on the first wave. Okay, so first wave is I'm talking about the thin film encapsulation. You can see the from the 2000, which is what I remember is the first the American group is looking at the water vapor permeation using the ALD. So that's I'm going to talking about the two topics: thinner barrier for the enhanced gas barrier performance. Okay, as you already know, why we need the thin film encapsulation for the OLED. Okay, let me skip over this one. But okay, need to conformal dense thin film deposition technology at very low temperature because of the OLED material is very, sensitive on the temperature. So we already know now is commercially this kind of the Vitex structures. Vitex is now gone, but this kind of the organic, inorganic stack structure, we already know this kind of structures very, effectively to prevent the diffusion of the water vapor. So this kind of the promotive and the initial thin film encapsulation is demonstrated the right side of the UM structure. However, that's very slow, and this is several chamber is simultaneously working on, and slow, expensive, no productive. So that's the right side is the plasma CVD silicon oxynitride, as well as the inkjet for the organic. So they're making the 3-layer to the sandwich structure to prevent the water vapor. But we already mentioned the automotive. This is very severe condition, like a high temperature, even low temperature, and 100% humidity. So we can, there can something like figure is problem anyway. So the reliability is a very critical issue in the automotive in thin film encapsulation. So that's the reason is the LG displays adapt the plasma ALD silicon dioxide as additionally to enhance the gas permeability. Okay, even though Mark didn't say about the code name, but I opened up the precursor name here. Yeah, that precursor is a DPARS. It's not the secret anymore. So the DPARS, actually this slide is what I bring in. Actually 5 years, I tried to screening not only these precursors as well as others, but this 4 is a representative. We testing any kind of the WVTL and the process, any the property. So finally, my decision is a DPAS because cheap. That's the problem, yeah. So and also I want to say is this kind of thin film encapsulation, gas permeability is the left figure is the general showing as a thickness thicker and the WV is goes down. But fortunately or unfortunately, even though you make the more thicker, we didn't expect the more like a low WVTL. There is saturated. So there is a many two kind of the like a mechanism, but I didn't mention about in detail. But seeing the right side of the the table like a figure, there is a quite shown the very different type of the WVTL behavior compared with the PCVD and ALD. ALD is the making the more thinner, but the WVTL property is the more better. You can see. So that's the we are expecting the like ALD simple encapsulation is a good for the like OLED OLED encapsulation. So that's the reason is to people thinking about the ALD's first wave to adopt the OLED application. And also, I want to mention about the another thing. Actually, we already know the oxide simple transistor is very sensitive to the hydrogen, like a diffusion or hydrogen-related defect. So the accidentally or like intentionally, we can deposit the like PCVD silicon oxide on the oxide semiconductor, but nobody used the silicon nitride directly because of the hydrogen. So this is the one of the reasons is the hydrogen is make the harm of the device degradation of the oxide semiconductor TFT. So this is the one of my the unpublished work. We are trying to the like a hydrogen permeability based on the ALD controllability. So they're looking at the bottom side of the as thickness increase, the hydrogen permeability is followed by the like a WVTL general the behavior. But interesting is the even same ALD material but different the hydrogen permeability behavior, which is the we have the chance to control hydrogen permeability by using proper material and the proper process. Okay, let me move on to the second wave, which is the actually I mostly devote the many years to develop the like challenging of the high mobility and the high stability in the oxide semiconductors. Because when I was in the Samsung, I actually the first pioneer to the picking up this oxide semiconductor in the site, Samsung Advanced Synthesis Technology. And finally, we got the oxide semiconductor has the potential. So I bring in that material in the Samsung display. And we starting this working in the Samsung display, that time as Samsung SDI. Okay. Let me say about this three category briefly. As you know, in the mass production level, the oxide semiconductor is already used by the PVD system. The PV is well matured and we can control exactly any kind of thing. However, mostly the active thickness is around 20 nanometers and we only control the oxygen gas flow as well as the annealing temperature. We have no option to change any process condition. If you want increasing the mobility or reliability, you should change your target or composition, anyhow other things. So this is very hard to get our optimized performance. But if you, right side is I'm suggesting the ALD is the possibility because of thin, and also the ALD can control the in-situ like a composition thickness as well as some interesting device performance. I show the later. So this is the general current behavior is what kind of material we are using. You can see the panel size, amorphous silicon is conquered all size of the LCD panel. If you go upside and if you see the right side, we want to need a more high current level. So we need a more high mobility in the transistor. And also we need a more power consumption because every type of the devices display move to the IT or mobile. So this is the power saving is a very critical issues. So the oxide semiconductor is well known is very low of current, which is we can get 1 hertz, the operation. That's the possible when you're using the oxide semiconductor. However, all oxide is now is our approaching is a real the target, very the harsh challenging issues. So maybe this slide is PDF. Yeah, I think this is not PPT. All right. So So if you can see, the many researchers try to enhance the mobility, but unfortunately, if you increase the mobility, there's a trade-off. We lose the reliability. So as time goes on, people try to increase the mobility, but unfortunately, still there is a trade-off. Our group is starting 2009 when I started the academy. We are looking at the ALD oxide semiconductor. Now I'm free. My boss is nobody. I cannot stop to working in this ALD research. So at that time, I go outside to find the new precursors. The precursor is most important for the ALD. So I developed a new indium precursors. Indium is one of the key elementary. So let me say about our research result using these 4 categories. I can say this 4 ALD value for the oxide semiconductors. So one is we can use the in-situ composition ratio to check any kind of the phase diagram, as well as we can control in the vertical engineering during the deposition initially. Third is the very critical issues. I'm going to show the later, but if you choose the A precursor and the B precursor, the same indium precursor, unfortunately, the chemical reaction is not 100% reaction. So there is a kind of some minor, we cannot see any kind of XPS, but there is definitely impurity inside here. So that's making some, the very interesting, result. The fourth is the very important part. I said is the sandwich structure. It's active and the insulator. Most kind of the device is the active and insulator, but there is no kind of the difference. Looks like a similar structure, but you can see silicon dioxide and also the hydrogen. So when you change the material and process, the interface of the hydrogen, diffusion and the diffusion out, that's totally different. Let's see. So, okay, yeah, the PPTs might, the sequentially showing up, but please understand this PDF file. So we are trying to find what I mentioned, 2009. I'm looking for the new indium precursors and push to the global precursor company to make the new indium precursors. They said, why? Too expensive. Where to use? So I, pursued the precursor researcher, and now indium is popular, but indium is looking at there is a lot of the indium precursors. You expected the same result, but unfortunately, no. Even carrier concentration and band gap, there is totally different. So that's one of the example. How about the IgGO is popular, IgGO to using these 2 phase diagram is the PVD. The ozone group is reported amorphous spaces and the carrier concentration. That too is the very the textbook for the beginner in the oxide semiconductor. So how about the ALD? We can make easily this kind of the phase diagram. So we are trying. So this is one of the example. We can change the composition combinatorial study, and you can see even usually 1 to 1 to 1 position is the optimized, is well done, but this is the totally different, a little bit, the upper way shift is optimized. And the one point interesting is the crystallinity. The IgG is well known is amorphous spaces. But when we design this kind of the ALD sequence, you can see there is the hexagonal C-axis aligned IgG, we can make it. So why is from the different? And what's the different performance? So the ALD is the many chance to looking at. So I'm going to show the one example how we can increasing the high mobility as well as the reliability. The first time we thinking about the the science papers, a single crystal, indium gallium zinc structure. So I'm designed the indium gallium zinc ALD sequence to make the single crystal. Yeah, no, that's right. We are deposition 200, they deposition 1,400, totally different. So we didn't make the single crystal. However, we tried kind of this, some element is embedded in the active layer, a vertical engineering. So we see more high mobility over the 70 That's the 7 years ago we achieved. But at the time, we don't know why exactly, why this boosting. And the right side is recently we are trying to change the different like process condition and the design. And finally, we achieved over the 100 mobility using the IGGO. This is the amorphous spaces. And you can see there's a TM. Maybe somehow we have to asking this kind of the like a laminar, like the structure. That is the really like a laminar structure. And the black and white, the black is the like a more heavy metal, like indium and gallium zinc. So we understand like atomically ordered layer, and that is the enhancing like the charge boosting to get like a high mobility, as well as you can see the like reliability is the reasonable value. Okay, the third wave is the most critical issue is we understand ALD is wonderful, but expensive, slow. How can you use for the mass production? Yeah, many companies, the engineers ask me, too expensive, too slow. Okay, we are going to how to solve that issues. The ALD is a sequential process. It's precursor purge. So that is in the one chamber and the changing about this kind of the cycle. But if you change the thinking, how about the like all gas flowing and if your substrate is moving on that like right side? So spatial ALD is one of the the possibility to solve that kind of the throughput issues. So the SALD, like a spatial ALD, is not my own idea. This is the like many groups actually try it, like the the US, Finland, Netherlands. Many people try to do this kind of the spatial ALD. Why? To enhance the throughput issues. So our group is have the like this. This is PPT. In PPT there is a moving. The movie there's a like a moving on that pictures. I'm sorry about that. Actually, I provided my 55, but yeah, there is something trouble. So the one is we can apply to this kind of spatial area to enhance the thin film encapsulation. Okay, only one, the aluminum oxide, but we can control the speed or the gap, also a flow. We made two type of the growth per cycle layer, and that is we can make the automatically. Different type of the layer. And this is one of the WVTL and the hydrogen permeability. So as you look at the bottom side, AD, which is the A, B, C, D is depending on the process condition, and that is the different density and the film property. So we can easily control about this kind of naturally different layer structure, which is the enhanced gas permeability and the control of the value of the gas permeability, and it's a high the speed. And this is one of the example. You may see the poster, and then the indium zinc aluminum oxide using the spatial ALD. This is also working very well, especially the mobility you can see around over the 30, which is the recently second level of the oxide semiconductor target. Also the display companies want to make it. So we can easily reach to that over the 30, actually more than 30 we have. So this is what I mentioned is the possible way. So let me summarize very fastly, I'm sorry. So the ALD is still, I mentioned about the very bright side, but still there is a dark side. Yeah, for example, we have the more high throughput and the new material ALD reactor, which is not challenging by the semiconductor field. For example, semiconductors never use the indium and zinc precursors. That is very critical and the dirty precursors. So that is the critical issues. Also, one other thing is the in-situ cleaning is the critical the issue in this ALD. For example, these kind of the element is of course, semiconductors never used, but they didn't think about the in-situ cleaning anyway. And also the fluorine is impossible somehow. So not only those kind of the issues, but also there's others. So we get together, like to solve this kind of the problem. Maybe the ALD has a more strong potential for the display application. Thank you so much.